Finland has solved the nuclear waste problem. Not we're working on it or we have a plan, but they've actually dug the tunnels. Let's talk about how they did it and why the rest of the world is watching. When you make electricity in a nuclear reactor, you don't get mountains of rubbish, nor do you get carbon dioxide for that matter, but you do get small amounts of very concentrated material, nuclear waste, which, as its name suggests, is radioactive. And you do need to do something with it, but what? Finland took that challenge and did something quite amazing. They picked stable rock that's been quietly minding its own business for nearly 2 billion years, tunnelled half a kilometre down, and built a geological repository designed to store nuclear waste for the long haul, without fuss and without supervision. It's called Onkalo, which is Finnish for cave or cavity, which I actually think is quite understated for something that's designed to outlast human civilization. And this is how they did it. Now, before we get to the tunnels and the copper canisters, we need to clear a few things up, starting with nuclear waste, which isn't really one thing at all. It's a family of things, and most of them, frankly, are actually quite dull. Most nuclear waste is so-called low-level waste. Gloves, overalls, bits and bobs of equipment that you would expect at any construction site, but just handled with a bit more paperwork. And then you've got the intermediate level waste, resins and reactor components, things that are more radioactive than low level waste and so require a bit more careful handling. But the star of the show, and what people normally mean when they say nuclear waste, is the high level waste. In practice, this means spent fuel, the assemblies that have been inside the reactor doing the hard work of nuclear fission and producing power. Now, here's a subtle but important point. High-level waste is small in volume, but it contains almost all of the radioactivity. Globally, it's only a few percent of the total waste by volume, and yet it holds the overwhelming majority of the radioactivity, about 95% of it, and that needs managing long-term. By contrast, low-level waste comprises 90% of the volume, but less than 1% of the radioactivity. The intermediate-level waste makes up the rest. And so when people talk about the nuclear waste problem, they're not talking about mountains of stuff that we have to deal with. They're talking about a very small volume of very concentrated stuff and exactly what we should do with it. Alright, here's the mind-blowing bit. This graph is the reason nuclear waste discussions always end up using phrases like geological timescales. Right after the fuel comes out of a reactor, it's intensely radioactive because lots of those fission products are still in their high-activity, attention-seeking phases. The good news is that these radionuclides burn through their mischief quickly. Over the first few decades, the radioactivity of spent fuel drops dramatically. In fact, it loses about 99% of its radioactivity in just the first 40 years, which is why spent fuel is stored for a bit underwater in giant swimming pools that, in the nuclear parlance, are delightfully called ponds. It's just physics-sanctioned procrastination. And it continues to fall rapidly over the next couple of centuries. Cesium-137 and strontium-90, which are two really common fission products in spent fuel, dominate the picture at this point. Their half-lives are about 30 years each, which means their activity collapses quickly. After roughly 300 years, which is about 10 half-lives, their radioactivity is diminished 1,000-fold. But then you hit this really long tail. After the short-lived stuff has mostly calmed down, you're left with a much smaller cast of much longer-lived characters. The long-lived fission products and the transuranics, plutonium, americium, neptunium amongst them, and other esoteric parts of the periodic table. These radionuclides do endurance, not drama. And that's the whole point of this diagram. Even as the curve keeps falling, it takes a few 100,000 years for the radiotoxicity to come down to the level of natural uranium ore. And so when people say we need a solution to nuclear waste, they do not mean that we just kind of put it in a drawer and forget about it and hope that people can still read the label in the year 12,000. The solution has to work on the timescales that this graph insists, not political cycles or generations or even the comings and goings of empires, but ice ages, geological time, which is exactly why geological disposal is such a compelling idea, because if your job is to keep a small amount of concentrated stuff isolated for a really long time, the best partners you can have are things that have proved they can sit still for billions of years. Rocks. Deep geological disposal is, I guess, quite an unglamorous idea at heart. You take the spent fuel, you package it so it's relatively stable, and then you put it underground into rocks that don't leak and don't move very much. Plenty of countries have talked about doing it, but Finland is the only one so far that's actually done it. And part of the reason is legal. Finland's Nuclear Energy Act doesn't let the country simply export the responsibility elsewhere. If you generate the waste, then you own the waste, and you have to do something with it. And that kind of changes the whole psychology of the situation. It becomes less what's politically convenient to do this election cycle, and a bit more, how do we actually solve this problem permanently? And after surveying sites across the country, Finland settled on Onkalo, an island off its west coast. I'm really sorry if I pronounced that wrong, by the way. On the surface, this island is quite unassuming. There are pine trees, low skies, the Baltic Sea, but it's actually one of the most energy-dense bits of Europe because of the 3 nuclear reactors that are there, which I actually think is quite amazing. But underneath is why we're here today. The subsurface. This part of Finland sits on nearly 2 billion year old crystalline bedrock, rock that's been cooked and squeezed and welded into something hard and largely impermeable, so groundwater just doesn't have that many easy paths through it. It's also a really, really long way from tectonic plate boundaries and comparatively steady, exactly the kind of place that you would choose if the design brief was, well, no surprises, please. Excavation began in 2004. The tunnels spiraled down almost half a kilometre underground, branching like a subway map designed by someone who really, really likes metamorphic rocks. But before anything goes underground, Finland turns the waste into something that you can bury with confidence, and that starts on the surface, in the encapsulation plant. Onkalo is the underground chapter, which we'll get back to. But the encapsulation plant is where Finland does the bit that looks a bit more like production line manufacturing. They take the spent fuel and they put it in sealed and standardised packages ready for burial. By the time the fuel arrives here, it's been sat in interim storage for a couple of decades, cooling off and calming down. The fuel assemblies arrive and are handled remotely, using heavy mechanical grabbers that look a bit like the giant versions of the things you find in a seaside arcade. They're moved into a heavy shielded fuel handling cell, where the assemblies are dried. And then along comes the star prop, the disposal canister. The canister is a 2-part design with 2 jobs. Inside is a cylindrical graphite cast iron insert, which provides the strength and holds the fuel in place. Around that sits a shell about 5 centimetres thick, made from copper, because copper is stubbornly resistant to corrosion in the chemical conditions you might get deep underground. These canisters are massive. They're about 1 metre in diameter, about 5 metres long, and they weigh in at just less than 25 tonnes. Radiation can be quite energetic at times, and it's actually plenty capable of breaking the molecules of air into its constituent pieces, and those pieces can sometimes recombine into undesirables, such as corrosive nitric acid or explosive hydrogen gas. Not exactly the kind of things that you want building up inside your lovely cylindrical container. And so to get around the problem, engineers fill the canisters with argon gas. Argon is gloriously inert. It just sits there and does nothing for the next few 100,000 years, which is exactly the brief. The weld is the last time anybody will lay eyes on the fuel, ever. And finally, the finished canister is sent to the lift, and from there, our story moves underground. The tunnel doesn't just go straight down like a cartoon mine shaft. It spirals, switchbacks, branches, offshoots, a deliberate descent to about 420 metres underground. And by the time you reach Onkalo's depth, you're surrounded on all sides by dense crystalline rock, the kind that doesn't do surprises. Down the lift shaft comes the disposal canister, and at the bottom it's met by a 90-ton robotic trolley that moves around the 25-ton metal tube like it's nothing. It trundles the canister through the tunnel network into the waiting lounge. One by one, the canisters are taken into the disposal tunnels and lowered into individual deposition pits. These pits are huge. They're about 1.75 metres wide and about 8 metres deep. That's deeper than most houses are tall. Each pit is lined with bentonite, and bentonite has a very useful habit. It's quite impermeable, but if it does get wet, it expands. And so if groundwater ever makes its way in, or I guess rather when groundwater inevitably makes its way in, the clay swells into any gaps and seals off the pathways. It keeps the conditions around the canister stable and limits any water movement. You can kind of think of bentonite as Onkalo's natural packing material. And if the canisters were ever to leak for some reason, then the bentonite would stop the radioactive material from moving outwards and beginning a new life elsewhere. Once the canister is in place, it's capped with more bentonite, and then the tunnel itself is backfilled and sealed. The goal isn't to pretend that water has been totally abolished. It's to make the whole system so tight, slow, and stubborn that anything down here stays put long enough for the radioactivity to all but vanish. In all, Onkalo's got enough room for about 6,500 tons of spent fuel, and it'll take until the second decade of the next century to fill it. And after that, the most important thing is that nothing happens. Now, here's one of the strangest parts. After all of this effort, after all of this amazing engineering, they don't build a monument to mark what they've done. They do the exact opposite. Onkalo is designed in a way that makes access difficult and isolates it from the surface. Finland's closure plan is that the access routes back to daylight get backfilled, meaning the vehicle tunnel, the shafts, and even the investigation boreholes all get sealed. And that gets you most of the way there, but then there's the human problem. It's reasonable to ask if there'll be a big warning sign there, something like, "Do not dig here," in 10 languages, perhaps with a skull and crossbones about the size of a bus chiselled into the local rock. And it is a comforting idea because it makes the whole thing feel tidy. Except that is not how humans work. If you make the warning too mild, then people will just ignore it, but if you make it too dramatic, then it turns into bait. I suspect that even if you chiselled a periodic table into the local bedrock and you slapped a big skull and crossbone over the 94th tile where plutonium sits, it would honestly just tempt people in, and not just the chemists. And we've been very good at ignoring warnings carved into stone already. Egyptian tombs came with curses, and we opened them anyway. Not because we're evil, but because we're curious. We just cannot stop ourselves. And there's a much deeper problem here as well. Even if you wrote the world's best warning sign, you're aiming at people in the far future. They won't understand your symbols or your alphabets or your language. They might not even recognise your concept of a sign. 10,000 years is plenty of time for religions to change, for cultures to come and go, and for civilizations to vanish. So Finland will backfill all of the tunnels, and then finally it will destroy the buildings on the surface. Because in the end, the best repository is one that doesn't require anybody to remember anything at all. If they don't come looking, then that counts as a success. And if they do come looking, then the best defense is that there's just nothing obvious to find. So, where does all of this leave us? First of all, Onkalo is about to become real. The tunnels are dug, the encapsulation plant is built, and the system has been running trial runs. And Finland is just going through the final few regulatory hurdles before they can start operations for real. Second, it works for the same reason that a good winter jacket works. Layers. The spent fuel is a stable ceramic. The canister is the main engineering barrier. The bentonite is there to swell, seal, and slow everything down. The bedrock is the last stubborn line of defence. None of them need to be perfect on their own. They just have to work together, which is the whole idea behind the multi-layer barrier. Third, Finland is not the only country doing this. Plenty of others are aspiring to have geological repositories too, including Sweden, Canada, China, France, and here in Britain. They're all at different stages, and they all have different geologies, policies, and politics attached, but they all follow the same general idea. And finally, and maybe most importantly, Finland solved the nuclear waste problem. And so, if you find yourself in two minds about nuclear power, or you kind of think to yourself, well, nuclear power's great, but what about the waste? Then Finland has an answer. It's small in volume, it's manageable, and there is a sensible end game. Nuclear waste is no reason to shy away from nuclear power. Thank you to Posiva, the company that built Onkalo, for letting me use their amazing footage in this video. I'll link to their website and their YouTube channel in the description. Go and check it out. If you want to dive much deeper into the science and the politics of nuclear power, I wrote a book about it. It's called Going Nuclear, and I link to that in the description too. And if you enjoyed this video, then I'm obliged to remind you that you might want to subscribe. This is quite a new thing for me, and so We'll see how it goes. Bye for now.